I've introduced the expectation maximization algorithm, and we looked at two flavors of EM, the hard EM and the soft EM algorithm. But one crucial thing we didn't actually talk about is, why does this actually work? Why does this actually improve my loss function or my objective? And I quickly want to explain that both for hard EM and for soft EM. Now, for hard EM, the reason is quite similar to what happens in k-means clustering. So let's just quickly recap k-means clustering. So in k-means clustering, I've got a bunch of points. They're all unlabeled. We don't know their labels. And we want to cluster them into groups. Okay, and each cluster is basically modeled by a particular mean vector. And k-means also alternate between two steps. So in the E step, what you do in k-means is you assign each point to the cluster that has the mean that's the closest to that point. So for instance, this point here, the closest mean is that point. So you would assign that point to that cluster, and so on and so on. And these points will all be assigned to that cluster. And then in the M step, you update the means so that they are the average of all the points that are assigned to that cluster. Okay, so what that would mean in this little case here is that this red point, this mean here, would probably move down because it would be the average of those points. In k-means clustering, both the E step and the M step is guaranteed to improve the k-means loss. Okay. And the k-means loss, you can just intuitively think of that as the sum of the square distances of each point to the centroid to which it's assigned, okay, to the cluster to which it's assigned. When you're doing the M step, when you're moving this mean down here, you're actually guaranteed to improve and make the distances to that centroid shorter on average, because you're moving it to the average of the points assigned to that cluster. So the M step is guaranteed to make these gray lines shorter. Okay. If it doesn't, then the mean will actually not move. It will just stay put where it is. And in a similar way, the E step, when you say, okay, listen, change the assignment of this point, you won't, but change the assignment from this point to this cluster, you will only do that. You will only change the assignment of a point to a different cluster if the distance to that cluster is shorter than it was before in the previous assignment. So again, you're guaranteed to improve the distance. Now, in a very similar way in hard EM, you're at every step guaranteed to improve your score of making a path through this hidden Markov model. Okay. So when you're doing the E step with a hidden Markov model and assigning your observations to states, you're only going to change the assignment of an observation to a different state if it actually gives you a better Viterbi score. If it doesn't, then the specific observation x little t, we won't assign another state to xt, except if this state gives us a better path through the hidden Markov model. Okay, so the E step is guaranteed to give you a better Viterbi score. And similarly, in the M step, when we're updating the parameters of our hidden Markov model, we are only going to change the parameters, for instance, of a state, if that's guaranteed to make the probability of observing our specific outputs higher. Okay. If it doesn't, then we're not going to change the parameters. Exactly like with k-means clustering, where we would only move a mean if it actually improved these distances. Okay, so I hope that gives you a feeling for why hard EM will improve your basically overall Viterbi scores. Now in soft EM, things get a little bit more tricky to prove in this kind of intuitive way. But there's a very thorough mathematical underpinning for the E step and these equations that I gave you for getting the soft counts when you're making your pass through your hidden Markov model. And similarly for the M step, there's very good mathematical underpinning for these maximum likelihood equations for getting the transition probabilities and the emission distribution parameters. Now, I don't want to go into full detail here about exactly why the fudge this is guaranteed to improve the log likelihood of the data, but I do want to give you an intuition for the mathematics that underpins the derivation of these equations. So this is just an intuition, basically a high-level sketch of what happens in soft EM. The aim of the game is really to improve the log likelihood. We've got some observed training data and we want to improve the log likelihood of the parameters given that that's the data we observe. So if we've got capital N training sequences, then you can maybe write out the log likelihood like this. So the log of, here we've got our parameters, and then we've got these sequences and we've got, capital N of them that we've observed, okay? Each of the sentences would have a different length, Tn. Okay, now it gets a little bit shaky, but you get the point, okay? Now, for many models, or not for many, but for some models, you can optimize this directly. If you've got a Gaussian over just like one observation, then you can optimize the log likelihood directly. But it turns out for hidden Markov models, it's actually a little bit tricky. The reason this is tricky is that to calculate this, we actually need to marginalize out the state sequence, okay? So we need to marginalize out all possible state sequences, okay, that we can follow for this observed sequence x1 to tn. That's our nth one. And then we've got a z1 to tn. And we need to marginalize this out. Now, and here's the crucial bit, the log of a sum is tricky to deal with, okay? And you can't just directly go ahead and calculate derivatives of this monstrosity with respect to the a's and the phi's in order to solve this problem and get a closed form solution. So the idea behind EM is to maximize a lower bound for the log likelihood, okay? So we're going to come up with some other function, and I'm not going to explain exactly what that function looks like, but that function is going to be a lower bound for this monstrosity, okay? That lower bound is called the elbow, the evidence lower bound. Now, the point is that the elbow is something that we can maximize in terms of theta, okay? But that doesn't actually help us that much, because let's say this is the log likelihood. This is the function that we're trying to maximize, but we're struggling to do it because of this sum here, okay? Now, just optimizing a lower bound doesn't help us. To just illustrate that very quickly, let's say we've got a lower bound for this function and the lower bound runs here, okay? This blue curve is actually a lower bound for the green curve, but that doesn't help me at all because maximizing this blue curve, ending here, ending there, that actually doesn't solve anything for me. How did that help me actually figure out the maximum of the log likelihood? It didn't, is the answer. Okay, so what is special about EM? And you were getting to the kind of the punchline of the algorithm, is that EM alternates, okay? And it keeps on updating the lower bound in a way. Okay, so let me just explain that to you. So let's say we guess an initial setting for our parameters, okay? And we guess that setting, let's say we guess it here, okay? So that's our first theta 0 at the very, very first iteration, okay? And if you run up here, then you end up somewhere there. Now what the E step does is it finds a lower bound for the green function, but crucially, that lower bound is tight at the parameter that we're guessing at the moment, okay? So what that means is that my lower bound could look something like this. And when I say it's tight, I mean that the lower bound at the point is on the log likelihood curve, okay? Not everywhere else, but on the point, this current guess for my parameters. So that's what happens in the E step. I update my lower bound so that it runs and it's tight at that point, okay? Fine. The M step, what that then does is it says maximize the lower bound, okay? Now, because the lower bound is tight at that specific point, maximizing the lower bound means that we're guaranteed to improve on the green curve, okay? In the worst case, if we maximize the lower bound, then the lower bound is tight. In the worst case, we would just stay at the same point, okay? If the maximum of the lower bound is just that point, then we would stay there. But in most cases, we are actually guaranteed to improve it. Okay, there's an absolute guarantee that we won't make it worse, okay? So we won't end up on a worse spot on the green curve. Let's just run through the algorithm and hopefully that makes sense. So E step, we find this lower bound. It's tight there. We maximize that lower bound. So that means that our new parameter setting would be at the maximum of that blue curve. So this would be our new parameter setting, our theta 1, okay, after like one iteration. So that was the M step, okay. Now we do the E step again. And what the E step does is it updates the lower bound, okay, to make it tight on our green curve, okay. So again, we end up with a lower bound, and maybe that lower bound runs here, something like that. Okay, M step, we update, which means we maximize the lower bound again. We end up, pretend that's a straight line. We end up there, that's theta 2. Okay, cool. E step again, we go there and we get a lower bound that's tight at that specific point. Okay, we maximize that one again, and so on. So each time we maximize, we're guaranteed to end up somewhere higher on the green curve than we were at the previous step. And I hope that intuition helps you understand why soft expectation maximization actually is guaranteed to improve the log likelihood. And I should say that if you go through all the steps, you derive the elbow and maximize the elbow with respect to your transition matrix and your emission distribution parameters, then you end up exactly with these equations that we saw before and that I explained intuitively for you for hidden Markov models. Basically, you end up with exactly these equations for the E step and these equations for the M step. Okay, so I hope you've got an intuitive feel for why soft expectation maximization improves the likelihood.